So to finish off with, we're going to look at our trig functions and then apply the transformations, so dilating and all that sort of stuff to our basic trig functions that we know. So we're going to look at, obviously, sine always comes first. So let's have a look at our sine curve. I'm going to just draw the basic sine curve. We know it has an amplitude of 1, so it goes up to 1, down to -1. So I'll plot that in. And when I'm drawing my trig curves, I like to mark in the boundary values of each of the quadrants and plot those points. So I've gone all the way up to 4 pi on the right-hand side, back to -2 pi on the left-hand side. And note, we tend to use radians now rather than degrees. I know that the sine curve starts at the origin, so I plot that one in first. And then the sine 90 is 1, so plot that point in. And then it's like a zigzag. Not that we draw straight lines in, of course, but I'll just plot those points in. So we go 0, -1, 0, 1, and so on, backwards and forwards. But it's a nice smooth curve between them all. And there's y equals sine x, our basic one. So what do we already know about it? Well, the domain is all real x. There's no breaks in the curve whatsoever. And the range in between -1 and 1. In general, though, we can now move it. So we can shift it up, down, across, whatever we like. So I've said the general one now is going to be a times the sine of bx minus c. So that's going to control shifting horizontally. It's going to control the dilation, because I could rewrite that as y over a, and I've also got a constant times x as well. So it's going to control all these things. Now, the period of a trig curve. So the period is how long do we have to go before the curve starts repeating itself. The reason I've put the period there on the amplitude is because it has to get back to the same point, but the curve also has to be going in the same direction. So to look at the x-intercepts can be deceiving, because if I start at 0, the next intercepts are pi. So you might think, oh, the period's pi. But at 0, the curve's going up. At pi, it's going down. So it's not in the same direction. So it's safer to pick another point to have a look at the period. So there it is, going from one peak to another peak. And it takes 2 pi. That's our basic curve that does that. So when it's in the form y equals a sine bx minus c, how's it going to change? Well, period is horizontal, so it's going to be about dilating the x value. We've got bx, so therefore the period will become 2 pi on b, because we're going to be dilating it. Well, actually, it'd be by a factor of 1 on b, because when we dilate, remember, it's x over the dilation factor. So 1 on b. So we might compress it in b or pull it out b, depending on whether b is bigger than 1 or smaller than 1. So when you see it, whatever the coefficient of x is, 2 pi divided by that coefficient will tell you the period. And then we have amplitude. So from the axis, how far up and how far down do we go? And normally that's 1. But now when we dilate vertically, we get y on a. So it turns out then that a will always be the amplitude. That'll be the dilation vertically. If I want to draw my SketchUp, the other thing I like to find are the divisions. Now, this is just something I do. It's not like it's an official formula or anything. But because I like to draw the boundary values, and in every period for a sine curve, there's 4 boundary values. So I divide by the 4. Whatever the period is divided by 4, that's what I'm going to mark the x-axis off as. Phase. What's phase? Phase is your horizontal shift. So when we look at this, and that's bx minus c, it's tempting to say that the shift is c, but it's not, because it's got to be grouped with the x. And at that stage, c is not grouped with the x because of the bx, so you'd have to factorise it, and it's actually b outside of x minus c on b. So the shift is c on b. Easier to think of it the other way. What would make that equal to 0? Well, x equals c on b would make that equal to 0. So there's your shift, or your phase. So phase is horizontal shift. What else can we tell? We can see the symmetry. It's got rotational symmetry, so we know it's an odd function. Therefore, it satisfies the rule for an odd function. Sine of minus x will equal the minus of sine x. So let's try and draw this one then. So we've got all sorts of things happening here. We've got a horizontal shift. We've got some dilation happening. So how would I approach this one? Well, the first thing I'd work out is what's the period? The period on this one, 2 pi divided by 9. So a really strange one. Amplitude, coefficient of the trig function, well, that's going to be 5. I work out the divisions next. So it's whatever the period is divided by 4. That tells me what I'm going to mark off on my axes. So now I can draw the axes. I know the amplitude's 5. I know I'm going to mark off every pi on 18. But there's also a shift happening here. Remember, the shift is grouping with the x. So the shift's not pi on 2, but for this one it would be pi on 18. All right, so let's draw it up. There's some axes. Amplitude, 5 minus 5. I'm going to mark off every pi on 18. It doesn't mean I have to label all of those. So you notice I've only labelled every second one. So pi on 9, 2 pi on 9 and so on. My sine curve would normally start at the origin. But this one is shifted pi on 18 to the right. So the first point I'm going to plot is there at pi on 18. And then I just do what I normally do for a sine curve. I would then go to the next division to the right, and I would plot at the amplitude, which on a normal one is 1, but on this one it's going to be 5. Once I've got those drawn in, I know the pattern. And so I just plot the rest of the points in. Now I go up and down, plot all the points in, and draw in a sine curve. But there's our curve. Y equals 5 sine 9x minus pi on 2. Cosine then. Let's have a look at cosine. I won't draw the basic one up again, but here's the general one. Y equals a cos bx minus c. What's happening here with all the shifts and everything? And pretty much the same. Remember, the sine curve and the cosine curve, they're basically the same curve, just with a shift happening. So the period is still going to be 2 pi on b. The amplitude is still going to be a. The divisions, when I mark it off on my axes, I'm still going to go period divided by 4. The phase or horizontal shift is still going to be C on B. So none of that has changed. Mind you, and I haven't drawn the basic one here, if you think of what the basic one looks like, it's an even function, not an odd function. So for this one, cos of minus x would equal cos of x. So we've got minus 4 cos x on 8 plus pi, and then plus 2. So this one, the negative, we've got a reflection happening in this one. And the plus 2, we've also got a vertical shift happening as well. Let's draw out all the important information. Period, 2 pi over, in this case, 1/8. So the period is 16 pi. The amplitude is still 4. It's not negative 4, it's 4. Because amplitude, we're just talking about a length. So it's like the absolute value, I guess, of the coefficient. We're just interested in the size. I'm going to mark my divisions. Well, 16 pi divided by 4 is 4 pi. And let's look at our shifting. We know we've gone 8 pi to the left. C on B, or another way of thinking about it, what would make the inside of those parentheses there equal to 0? And that would be negative 8 pi, and that's why it's to the left. We know we're going up 2 because of the plus 2. And so the negative out the front tells me that the curve has been flipped as well. So it's upside down. We've got all of that happening. All right, let's draw it. Axes, first thing we need. Now I'll mark in, you'll notice, a horizontal line at 2. That's the first thing I did on this one. So the whole thing's been moved up 2. So I'm not going to be winding my cosine curve around the x-axis. I'm going to be winding it around that horizontal line that I've drawn in, y equals 2. Notice I've dotted it in. It's not a solid line because y equals 2 is not part of the solution itself. It's just there so I've got a reference point. Now our amplitude was, where is it? There it is, 4. So I go up to 6, down to -2 in this case. Horizontally, I'll mark off every 4 pi. Again, I haven't labelled every 4 pi, but I've marked off every 4 pi. Where do we start? It's a cosine curve. If I was drawing our basic cosine curve, at x equals 0, I would be up at the amplitude. I'd be up at 1. All right. So that would be the first point I plot. So for our one, I'm shifted 8 pi to the left and up 2. So the first point I would plot would be at -8 pi, but it would be at the amplitude, which is now shifted up 2, which is at 6. But we have the additional thing of being upside down as well. So instead of plotting at the top, I'm going to plot at the bottom. So let's put that first point in. There it is, -8 pi minus 2. Okay, I move to the next division. For a cosine curve, I would be at the axis. But this time, it's shifted up 2, and that's why I've got the horizontal line in. So now I'm going to plot on the new axis. But then it just repeats that pattern. So we're going up and down, and I can draw in my cosine curve. And we have our curve, y equals -4 cos, x on 8 plus pi, plus 2. Well, it wouldn't be complete unless we looked at tan as well. So let's do tan. The general one, a tan bx minus c. So what's happening with this one? Be careful. Period is pi on b now. Because our normal curve, the period is pi, not 2 pi. So pi divided by b, so we're taking into account the dilation on the x. So pi on b units. You notice I haven't bothered with amplitude. Think about your tan curve. It doesn't have an amplitude. It goes off to infinity in one direction and negative infinity in the other. So when we're talking about a tan curve, amplitude's meaningless. It doesn't have one. Well, how would I mark my divisions? In this case, it's period divided by 2. Again, that comes back to if I was drawing the basic curve and you think about how many divisions I would mark off. So just like the period is now pi instead of 2 pi, marking off my divisions becomes period divided by 2 instead of period divided by 4. Phase is still the same though, so the horizontal shift is still the same. It'll be C on B. Again, we've got to use our imaginations here. Think about tan x, odd or even. It's got rotational symmetry. So it's an odd function. We know tan of -x is equal to minus tan x. Let's draw one. Let's throw in some irrational numbers there. Y equals e tan pi x minus 2 pi. The reality is it really didn't matter what I put in front of the tan function, because remember, amplitude's meaningless with the tan function, so I put e there. The only time it really comes into effect is if it was a negative number, because then we know we'd have a reflection. Period. Pi divided by pi. Period's just 1 for this curve. So I'm going to mark off a half. So horizontally, I'm going to mark my divisions off at a half. But what have we done with this curve? We've shifted 2 to the right. So that's my horizontal shift. Remember the easy way of doing it? Look inside the parentheses. What would make that equal to 0? So pi x minus 2 pi, well, x equals 2. So I know I've shifted 2 to the right. Let's draw my axes in. So I'm going to mark off half. So let's put them all in. There's all my divisions, label them. Again, I haven't bothered labeling all of them, but I've marked in 1 and 2 there. Now, what happens with a tan curve? If I was drawing a tan curve, I would start at the origin, but this one's shifted 2 to the right. So I'm going to start over there at 2. Now, when we're drawing the curve, what does the tan curve do? Well, it just alternates. It goes x-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote. So let's put that pattern in. There's an asymptote on the right. Now let's go to the left. So we've got asymptote, x-intercept, and so on and so on. Okay. Now our tan curve, no, we haven't flipped it upside down. the E doesn't matter because there's no scale on the y-axis, so I can still just draw in my standard tan curve. So there it is. And I'll repeat that between all of our asymptotes. So y equals E tan pi x minus 2 pi. As I say, with the y-axis, there's no sense of scale on this. And it's one of those curves where I don't really worry about it unless we needed to use the graph for something. So if we were going to look up, say, tan pi on 4 was equal to, if it was the basic curve, it'd be equal to 1, then, okay, possibly I need some scale there. But for a sketch of a tan curve, we don't normally label anything on the y-axis. Oh, 3J. So you're just going to draw some trig curves, but now it's not just a basic trig curve. We're going to do some transformations to it. So it might be a shift horizontally, it might be up or down, it might be a dilation, it could be a reflection, but any of those ideas that we've been looking at.